Hello, everyone. This is our class number 23. We're going to go over our first unsupervised learning model, which is used for dimensional reduction, and namely principal component analysis. PCAs it's one of the oldest methods out there. It was developed 1901, so it has 120 years background, and it's well developed, and it's very powerful. And the basic idea is very simple. However, the mathematics behind it, it's a little challenging, especially if this is something that you're saying for the first time. And it needs a little bit of background in algebra and mathematics. But I hope that with the visualization that we're going to go over, you get the big picture of it. Don't lose perspective. Don't lose in the formula. Just try to get the big picture, and hopefully the visualization is going to help you to solidify the idea. Okay, so let's look at this simple example. Imagine this is our data set. And guys, in machine learning in general, always when you see a plot in two-dimensional or three-dimensional, always pay attention to the labels, right? So what do we have here? This is our feature space, right? This is our feature space. So I have the feature space is in 2 dimension. And look at that. Do you see any colors here? No. Why? Because the data is unlabeled. We don't have the target variable. So this is my data set. X1, X2. That's it. There is no Y variable. So I cannot think of it as a regression question. I cannot think of it as a clustering classification problem because the data is not labeled, right? So there's no color on these dots, right? Circles. So what can we do with that? So principal components analysis, it's in general, in unsupervised learning models, because we don't have a response variable, we are not interested in predictions. We are not interested in making some predictions. All we care, the goal is to discover some patterns in the data. The goal is to see if we can extract some interesting information from the data itself, from the feature space itself, right? And for example, and how in an informative way we can visualize the data, the feature space. Or maybe if we can discover these subgroups among the data, right? So imagine I can say maybe these observations behave similarly, these observations behave similarly, right? So these are all unsupervised learning models, right? There is no label, there is no target variable. So one of the methods that we use for dimension reduction is called PCA. And the PCA in a nutshell, so we're going to go over the details later on, but in a nutshell, looks for the most variation in the data set, right? So for example, if I just show you this data set and I ask you, but just stare at this data set and tell me, I'm going to label them. So let's call them vector number 1, direction number 1, direction number 2. Which of these directions are going to explain the most variation of the data? 1 or 2? 2. Does everyone agree that it's 2? The data is, look at the variability of the data set. So if you go along the axis number 2 here, you agree that the variation is going to be higher. Look at this distribution, it's wider. So it means that the variance is higher along that line, right? So for now, again, this is just a big picture. Let's call it principal component 1. And the other one, let's call the other one principal component 2. So this is basically, in a nutshell, what principal does to your data. It's going to sort the axis of the new feature space that the variation of the data is maximized, right? Now, our goal today is to see how we can do that mathematically, because visually it's easy, right? We can look at the data and say, okay, at this axis, the variation is maximized. And but when it comes to practice, we don't know why it's not this line, why not this line, right? And if you have millions of observations, maybe it's hard to visualize, right? Maybe PC1 and PC2 or numerically are very close to each other. So which one should we pick as a first principal component, and the next one is going to be orthogonal to the first one, right? So that's the goal that's the plan for today. But again, in a nutshell, through the end of this class, do not lose perspective. This is all we're going to do by the end of the class. Look at the data set and summarize the data set in a new feature, in a new coordinate that is going to summarize the data by the variability in that direction, okay? The variance in that direction. Okay, so we started our journey in unsupervised learning models, and remember, there is no target variable. And the first set of groups of models that we're going to look into are dimensionality reduction ones, and for unsupervised learning model. In this class, we're going to only cover the PCA. Guys, remember, we talked about dimensionality reduction somewhere else as well. Do you remember in this penalized regression, we had lasso? Lasso was also used for reducing the dimension of the data. But this reduction is different than this reduction. In what sense? So here, for example, I have, first of all, this is supervised. Lasso was supervised, so there was a target variable, right? But beside that, if I have x1, x2, up to x10, we ended up reducing the feature space by, let's say, go from 10 to 2, right? So I may end up with working x1 and x5. Does that make sense? So at the end of the day, we got rid of a bunch of features in the data set. However, in the unsupervised, in the PCA methods, if I have x1 through x10, we may end up with two principal components. So the dimension reduced from 10 to 2, but each of these principal components are a linear combination of, this is key, all the feature space. Does that make sense? So this is a big difference between the two, right? Just pay attention that when you hear the term dimensionality reduction and you don't care about the target variable, and then you wonder, okay, should I do lasso or should I do PCA? Just be aware that they are very different, right? And we usually go with the PCA because it's a linear combination of all the features. You don't necessarily end up dropping maybe some of the important factors. Okay, so that was a big difference. Then next class, we're going to go over the clustering methods, and we'll discuss the clustering method in next week. Okay, so topics for today. We will revisit what's the definition of unsupervised machine learning, and then we'll look at some terminologies about principal components in general. So we will be, namely, we're going to look at what is the definition of eigen things, eigenvalues, eigenvectors, and things like that. Then when we're ready to move on to officially define what is principal component analysis, we will go over that. Then we are going to rank the principal components, and based on the contribution of the components to the variation of the data, we're going to come up with some plot called it Scree plot. And then finally, we are going to discuss why principal component analysis, what are the pros and cons, and most importantly, what are the applications? Because unsupervised learning models necessarily, you're not making any prediction with them, right? There is no target variable. So you may wonder, so what's the point of doing it on unsupervised machine learning? So this part is going to be very exciting, and you'll see what are the applications of PCA. So most of the time we use PCA and as an EDA part in the data analysis, right? Explanatory data analysis. And we extract some information, and the output of the PCA is going to become the input of your supervised learning model, right? So this is going to be very interesting, right? So at the end of the day, the PCA is going to help you, for example, reduce the dimension of the data and then apply KNN, k-nearest neighbor, reduce the dimension of the data and then apply logistic regression, whatever, right? So that's, just keep in mind that yes, sometimes unsupervised learning models per se, they don't have any applications, but in combination of supervised learning models, they are very powerful. So that's what we're going to do. Okay, so let's start with revisiting the definition of unsupervised learning model. Unsupervised learning is a machine learning technique that does not use labeled data, right? There is no Y variable, there is no target variable. So the goal is to discover the underlying pattern and find groups of subsamples that behave similarly. Look at this two charts here, right? On the left, it is supervised. Why? Because, and pay attention to the axis, both of them x1, x2. So we have two features. The one on the left is supervised because it is color coded. So it means that there is a target variable. The target variable Y. So if x1 is this, x1 is x2 is that. So maybe Y is blue or red. Blue or red, right? So this is supervised. This is unsupervised, right? Does everyone see that? Because there is no label. So what's the goal here? We want to see if we can come up with some finding some underlying patterns in the data. So it seems that the observation in this cloud of the data are behaving in a similar way, and the observations here are behaving in a similar way. This is really interesting observation, right? Because at the end of the day, we're going to combine this, for example, PCA, and with the clustering method, say that, okay, you know what? Maybe we need 2 clusters in the data. Maybe we observe 3 clusters in the data, right? Because next class, when we are going to work with k-mean clustering algorithm, one of the caveats is that you have to figure out what is k. Well, if you do PCA, maybe it's going to give you some more information that what should be the k, right? Instead of doing cross-validation, at least for the data set, which is, you can visualize it in 2 dimensions, right? But I just want you to be aware of the capabilities of PCA. Okay. The 2 main types of unsupervised learning algorithms, as we discussed, is the first one is dimension reduction algorithm, namely PCA. And the second one is clustering techniques. No, we're going to go over k-mean clustering and hierarchical clustering in general. Okay, now let's talk about eigenthings. If you haven't seen eigenvalues and eigenvectors before, I want you to pay very good attention. I want your 100% concentration with me, because these topics, especially if this is the first time that you're seeing, conceptually it's a little challenging, but I will show you some visualization, and hopefully it's going to help. We're going to start from a very, very basic idea of what is eigenvector, right? So very informal definition. Eigenvector is a vector that does not change direction. So it's a vector that does not change direction in any transformation. Okay. So look at this picture. Oh, let me minimize this. So if you look at this picture and imagine you're going to do a transformation, right? And I will be specific what do I mean by transformation, right? But for now, just look at it very simplistically. So we are transferring the data from the one on the left to one on the right, right? Let's say I'm keeping track of 2 vectors in the data, the blue and the red one, right? I want you to just stare at the blue and the red arrows after the transformation, and then answer this question: which of these 2 arrows are going to be eigenvector? Look at that very simple definition of eigenvector. The blue one, right? Does everyone agree that the blue one does not change direction after the transformation? Okay. So this is called eigenvector, because after any kind of transformation, the direction of the vector is not going to change. And it is the simplistic definition of eigenvector, right? So we're going to make it complicated step by step. So this is the eigenvector, and the magnitude of the eigenvector after the transformation is called eigenvalue, right? So now you said that the blue one is eigenvector. Can you tell me what is the eigenvalue? Look at the magnitude of the blue one before and after transformation. Does it change? So what do you think is the eigenvalue? 1. Does everyone see that? So this is the blue. If the blue was something like this, the eigenvalue was 2. If the blue one was something like this, the eigenvalue was -1. Do you follow? Okay. So now in its very simplistic form, we know what is eigenvalue, what is eigenvector. So eigenvector is a vector that if you apply any transformation to that, it's not going to change direction. But its magnitude may change. And there is a corresponding value for that magnitude, which we call eigenvalue. Okay, so that was the basic definition. Now, what is this transformation? So let's figure out what is that transformation. So in this mapping, we already answered this question, right? The blue arrow is eigenvector. Why? Because it did not change direction after the transformation. Eigenvalue is 1. Why? Because the magnitude didn't change. Okay, so let's become more formal. So formally, how do we define eigenvectors and eigenvalues? We say for a square matrix A. What is a square matrix? So 2 by 2, 3 by 3 is square, right? So 4 by 4. For a square matrix A, an eigenvector and eigenvalues are defined as below. So this is the formal definition of eigenvalue and eigenvector. So what do we have here? It says that if you apply any transformation, so A is a matrix. I'm going to show you that each simple square matrix that you know, so for example, this 1, 2, -1, 3, this is a transformation. Oops. This is a transformation, right? And we will visualize it. Why? What does it mean? So it means that if I apply this simple matrix to a vector, it's going to transform it. It may transform both the direction and the magnitude, or it may transform only the magnitude, not the direction, right? So each matrix A, we call it transformation matrix, and it must be the squared matrix, right? If I apply that transformation to a vector, and the direction of the vector doesn't change. Remember, lambda is a scalar, so we call it Eigenvalue. This is our Eigenvalue, so it's a scalar. So 1, 2, minus 5, minus 0.2, and etc. Right? And multiply v. As you can see, the direction is the same. So the direction of AV and lambda v is the same. But, so the idea is that, so if I wanted to say it in simple English, Eigenvector is a vector. If you apply any transformation to that, it's not, the direction is not going to change. The only thing that may change is the magnitude. Does that make sense? So far, you're clear on the definition of eigenvector and eigenvalue. The only thing that's unclear is that transformation. What do you mean that the matrix is transformation? So let's see what do we mean by that. But before that, let me visualize this eigenvector and eigenvalues for you. And so what we're going to do in this exercise, we're going to see V and AV and the transformation of that vector. And then we're going to look at the eigenvalues. So here's, if you click on this, let me see. If you click on this picture, it's going to navigate you through a very cool visualization that's going to help you understand more what is eigenvalue and what is eigenvector. And after that, we will be talking about transformation matrix. Okay, so I cannot write. I think I cannot write on this one. Okay. Let me see if I can write on this. Annotate. Okay, cool. All right. So this is my A matrix. This is my A matrix, the transformation matrix. We're going to see. So if I apply this matrix 1, 1, minus 2, 4 to any kind of vector, it's going to transform that vector from space to another one, right? So let's see how do we do that. So for example, if I say, so A is 1, 1, minus 2, and 4. And I want to multiply it by V. Let's say my V is here. So this is my V. Right? And V is 1 and 0. Does everyone see that? It's 1 and, yeah, it's 1 and 0, right? So this is a vector 1 and 0, right? So if I apply this transformation to that vector 1 and 0, so what do I get? So I get 1 and minus 2. You agree? This is a simple matrix multiplication. So it seems that if I apply this transformation to this vector, it's going to send it somewhere else. Where is that somewhere else? 1 and minus 2. Find the 1 and minus 2, we are here. The red arrow is my A multiply V. So the red arrow is a transformation of V under the A transformation matrix. Does that make sense? No? Okay. So for now, I want you to think of A as a transformation matrix. And as you can see, what does that mean? It means that if you apply this transformation to any kind of vector, it's going to move that vector somewhere else in this set, right? So it's going to take this vector 1 and 0 and move it to here, to this red one. So after that transformation, so if I change the V, this transformation is going to send it somewhere else, right? So let's go ahead and change the V. And I want you to pay attention to so I'm going to go ahead and change the V, and then you look at the AV, the red one, right? So here's how it's done. I hope that this works. Wow, it's annotating, sorry. So let me clear all the annotations and then, right. You see, if I change the V, and then apply the A transformation, the matrix A transformation, the AV is going to change. Are you following? Right? And pay attention, there are 2 times in this setup that AV and V are exactly in the same directions, right? Look at that. So one of them happens here, right? You see that the direction is the same? The other one happens here. Direction is the same, right? How many eigenvectors do we have? 2. Does that make sense? So then, let's talk about the magnitude. Let's start with this one. what do you think the eigenvalue is? Roughly speaking, I don't want you to think of the exact number. Okay, maybe 2 or maybe 3. Let's see this one. Maybe 2 more. I think one of them is 2, one of them is 3. So let me show you the eigenvalues. So the eigenvalues are 2 and 3, right? So in one of them, the magnitude was 2 times the vector v. In the other one, the magnitude was 3 times the vector v, right? So as you can see, if I apply any transformation A, which is here, right, 1, 1, minus 2, 4, to a vector, if I can find a vector that does not change direction, that vector is called eigenvector. So this is eigenvector 1. This is eigenvector 1. So I have 2 eigenvectors. What are the corresponding eigenvalues? 2 and 3. And I can turn on the trace and show you. So this is my one eigenvector, and the other one is this. And now you can compare the value, right? So here 0.7 is 0.14 is 1.4. So this is eigenvalue 2. Eigenvalue 2. And the other one, this must be my eigenvalue 3. -7. Yeah, I don't know, but maybe there's something with this visualization, but you get the idea. If I change the transformation matrix, I get a different number. Does this make sense? What is the concept of eigenvalue and eigenvector? If I go to 3 dimension, at most I can have 3 eigenvector. If I go to 4 dimension, at most I can have 4 eigenvectors, right? So at most you can have the number of dimensions eigenvectors. But can it happen that, for example, the dimension is 3, I only come up with 1 eigenvector? The answer is yes. Can it happen that the dimension is 2, there is no eigenvector? Yes, right? Let's try another transformation. For example, let's do 1. I don't know, I'm trying to come up with something that doesn't have an eigenvector. Well, this one has another 2. Maybe if I do these are, happens to have, let me do minus. Well, I cannot calculate eigenvalues off the top of my head, but I think if I do 1, 1, 1, 0, simple transformation to 0, 1, or shear transformation, if I change it, it's going to be. So here's a unique eigenvector, right? So if I imagine your transformation matrix is 1, 0, 0, 1, what is it doing? Nothing, right? It's basically multiply. If I multiply to any vector, I get the same vector, right? So look at that. Do you see that V and AV are overlapped? So what is eigenvalue? 1. What is eigenvector? That V is the eigenvector there, right? So if I just turn it around, it's going to be, eigenvector is going to be always, the eigenvalue is going to be always 1, right? And there are lots of those eigenvectors. Okay, so hopefully in terms of visualization, you understand what is eigenvector, what is eigenvalue. So we know that there are thousands of vectors out there, but only in this case, 2 of them are eigenvalues, because when I apply that transformation, matrix A transformation, the direction is going to be the same, right? Now, finally, let's talk about that transformation. So here is this is a link from Khan Academy, but the video is provided by 3B1B. Do you know 3B1B, 3 brown, 1 blue? This is awesome. If you like algebra and mathematics, this is an awesome YouTube channel with, I think, 1.5 million subscribers. This is really cool, especially if you're into visualization. So now let's talk about that transformation. The matrix, so I was telling you that any squared matrix is a transformation. It can take a vector, send it somewhere else, right? So, for example, I want you to pay attention to this transformation. Look where the where the green arrow is and where the red arrow is, and what happens after the transformation. So it kind of rotated, right? So look at it one more time. Do you see the rotation? So let's see how we can do this transformation using matrix algebra, right? So our green was, look at the, let me pause it. So where's the green? Right now, the green is at 1, 0. Does everyone agree? 1, 0. So before transformation is 1, 0. After transformation is what? 0, 1. Very good. So this is going to be the transformation for the green one. You see that? This one, 0, 1. Right? What happens to the red one? Red initially was 0, 1, and then it becomes what? Minus 1, 0, right? So my transformation matrix is going to be 0, 1, minus 1, 0, this one. Does everyone see that? So this transformation is going to rotate the axis like this, right? And it's not always rotation. We can squeeze it. We can, we can push it forward, backward. It's called, yes, squeeze, squish, things like that. So we can play around with that transformation. So this was one example, and our A transformation matrix was 0, 1, minus 1, 0. Does everyone see that? How did that happen? Okay. Now let's do some exercises together. I want you to look at the transformation and then figure out what is the correct. So the lighting is not good in the class. Let me turn off the on the curtain. Okay, I want you to pay attention to the transformation and try to figure out which of these ones are correct answers. Is the question clear? Okay, so pay attention to this one. So what happened? Look at it again. It's not only rotation. So A, B, C, or D. Give it a try. Look at A, B, and D. Both of them off the diagonal, it's 0. So whatever it is, it's a rotation. So we need to, this is something more than rotation. It's called a smear, right? So look at that. So if you apply this matrix C to the green and red vector, it's going to become the new one, right? So this is the correct answer. You couldn't grade your answer. It looks like you left something blank. Did I? So that's the correct answer. Let's do a bunch of other ones. So actually, I'm going to do this one, the last one, because it's more challenging. Let's do this one. What happened? That was easy. Which one is the correct answer? Do you agree that both green and red shrunk? So which one is the answer? C, right? Okay, very good one. So now let's look at the next one. Let's look at it one more time. Maybe one more time. What is happening here? Well, it's not A, right? Yeah. And it's not C. It's either B or D. Okay. Why? That's correct, right? Because it kind of flipped and went back to its own place. And then let's see, what else do we have? This is also easy to figure out, right? Look at the options. Which one is it? D, right? Does everyone agree? Okay. Yeah, I will do one of them, yeah. And then let's do a couple of more, make sure that you're all on the same page. Because I want you to get the idea that, so this kind of rotate everything, right? So look at it again. No, the green was there and then completely changed to the negative side. So if anything, that would be B, right? Okay, and the one that we didn't, actually, the one that we didn't was the easier one. I think it was multiplied by 2, right? Yeah, this is just expanding, okay? So this is A. Which one do you want me to do? Maybe the smear ones, right? Some more difficult ones. Any of them? So let's see. Let's do this one as an example, right? So what are we doing? We are looking at. So first of all, let me see if I can annotate here. So my green arrow is 0, 1, right? Sorry, 1, 0. I cannot erase. So the green arrow is 1, 0. And what is the transformation? -2, 0, -1, -1. You do the math. What do I get? -2, -1, right? So then it's going to go to -2, -1. It's going to come here. My green is going to become some here, right? After the transformation, right? Look at that. Each transformation matrix is just transforming your vector from one place to another place. Sometimes the direction change and the magnitude change, like this. Look at the green one. Both the magnitude and the direction change. So can I say that the green one is eigenvector? No. The red one, same story. So if I play it, this is where the green one, right? Does that make sense?
So is it always based off the green one?
Oh no, you can apply transformation matrix to any vector, right? Actually, apply it to many vectors, and only 2 of them will not change the direction. We call them eigenvectors. So, for example, for this matrix, for this matrix that we have here, let me write. We can calculate eigenvectors by solving that equation, mathematical equation, right? And then the eigenvectors are going to be a vector that if I do this transformation, the direction is not going to change. I hope that's clear. Okay, so let me clear all and go back to the slide. Where is my? So now we know what is eigenvector, what is eigenvalue, and we can, for example, use this formula to calculate the eigenvectors and values of a transformation matrix. So all that matters is that what is your transformation matrix? For any squared matrix, you can calculate eigenvectors and eigenvalues. Eigenvectors are the vectors that do not change direction if you apply that transformation. Eigenvalues are the magnitude of the eigenvector after that transformation. Okay, are we good? This is important because if you don't understand this part, the PCA is going to be a little challenging. We can spend a couple of more minutes here.
Can you introduce on the previous slide but you started going over like trying to explain the matrix.
Okay, so let me find some white space. What are we doing? At the end of the day, do you remember I told you that do not lose perspective? This is my data, x1, x2, right? What's the goal? The goal is to come up with these 2 new axes. I need to somehow rotate, smear, whatever, squeeze the axis somehow, right? Based on some transformation matrix. This is how eigenvalues and eigenvectors are going to play, useful, right? So at the end of the day, I want to transform this coordinate system to this coordinate system, call it PC1, PC2. And we're going to normalize thing, and it's going to be around maybe here, right? So that's why we're going to use eigenvector, eigenvalue. So all that matters is that we can calculate eigenvectors and eigenvalues for a matrix, for a squared matrix transformation, right? Transformation matrix. So this is a mathematic part. When it comes to machine learning, that transformation matrix becomes what you're interested in, right? So let's see what is that A matrix that we are interested in this sense, right? Actually, I'm going to ask you, do you have it? Let's see if you can make a guess. Now let's connect the principal component terminology to the principal components to eigen things, the one that we just covered, right? So eigenvectors and eigenvalues of a covariance matrix represent the core of PCA. So why do you think that that transformation matrix that we're looking for turns out to be our covariance matrix? Let's call it covariance of our data frame. And data frame, I'm looking at the feature space, right? So let's call it covariance of capital X feature space. Because remember, guys, what we were doing was something like this, right? So this is, do you remember that I told you that you're interested in finding the components that explain the variation of the data most? So I already talked about variance. So if any transformation matrix is out there I'm interested in, and it comes to principal components, that's a covariance matrix. Because I want to see, so what is covariance matrix? This is my covariance matrix. I have, let's say it's 2 by 2. So I have variance of x1, covariance of x1 and x2, covariance of, well, sorry, this is x1 and x2, this is x2 and x1, but they're the same, right? And then variance of x2. This is going to be our transformation matrix. So I hope that you can connect the dots. What is the relationship between eigenvector values and principal components? Because in principal components, we do care to summarize the data in new dimensions, in new space, in new feature space, that it's basically rank the components based on the variability of the data, based on the variance of the data, right? Now, let's see. So if you know the concept of principal components and eigenvectors, I think the rest of it should be straightforward. Okay. Consider the following data points. So here, imagine we are in x1 and x2 space. So you can call it x2 because we want to make sure that this is our feature space and we're consistent in the terminology. And this, we want to transform this, right? We want to find a direction or directions, depending on how many eigenvectors we have, eigenvalues we have in the data set that explain the most variation, right? So our transformation matrix will be the covariance matrix. I hope that this is clear why we do care about the covariance matrix. So that's a squared matrix, right? We need to, the transformation needs to be squared, so I cannot work with the variance. We had to be squared. Okay. So what are the directions? So this is my original data. This is the data in the new coordinate system. New coordinate system is PC1, PC2. And so if I ask you which one is PC1, which, well, you're looking at the answer, but do you agree that the variation along this line is more than the variation along that line? So that's how how the principal components is going to end up do the job. So it's going to, PC1 is going to be the axis, that the direction that we have the most variation. PC2 is going to be the direction that we have the next most variation, but it's going to be orthogonal to the first one. Why orthogonal? Because we want to make sure that the components that we're figuring out are uncorrelated with each other. So in linear algebra, when two vectors are uncorrelated with each other, they are perpendicular, right? Because the cosine between the two is 0. Okay. So the principal component one is whatever it is. The second one is orthogonal. If you go to 3 dimension, the third one is orthogonal. If you go to 4th dimension, we cannot visualize it. But the beauty of this is that now, instead of working with x1, x2, x3, that maybe they're correlated, we're going to work with maybe only 2 of the principal components, but we know for sure that they are not correlated with each other. The correlation is 0. Okay. All right. So the principal components, eigenvectors of the covariance matrix, determine the direction of the new feature space. As you can see, this is the direction of the new feature space. And the eigenvalues determine their magnitude. Okay. In other words, the eigenvalues explain the variance of the data along the new feature space, feature axis. Does this make sense? This is all what we do in terms of principal components and how we can connect the principal components with eigenvectors. So I can sum it up like this. Principal component number 1 is the eigenvector of matrix A, the covariance matrix, which has the highest eigenvalue, the largest eigenvalue. Why do I care about the largest eigenvalue? Because that's explained the most variation in the data. All right. So here's a question for you. If you want to reduce the dimension of this data set, we have x1 and x2. If you want to reduce the dimension to 1, which principal component would you drop? 1 or 2? you drop 2, right? Because everything is explained in one direction, in PC1 direction, and then after that, in PC2. If you end up dropping anything, it's going to be PC2. So I can say, for example, if it is two dimension, I can say maybe 70% of the variation is explained by this one, 30% is explained by this one. Are we good? You end up, so instead of working with 2 features, you end up with working with 1 feature. That 1 feature is a linear combination of x1 and x2, and it's able to explain 70% of the variation of the data. Of course, it's not 100%, it's not perfect, but it's going to help you a ton. You know, just look at it, the big picture, going from 200 features to 5 features. Think of it this way. And we are going to look at an example from the CFA reading, going from 2,000 dimension feature to 3. Now it's really shine. And you will see that only the first 3 components are going to explain 85% of the variation. So who cares about the rest of 15%? Because we are saving 1,997 dimension, right? What do we lose? Interpretability. PC1, PC2, PC3, these are linear combination of 2,000 features. There's no way you can interpret that. Very good. So in summary, principal components are vectors that define a new coordinate system, right? And in which the first axis goes to the direction of the highest variance in the data. The second axis is orthogonal to the first axis. And if there's 3 dimension, the third one is going to be orthogonal to the second one and first one, and et cetera, et cetera, et cetera. Okay, so this is our real data, panel A. By the way, I took this one from the 100-page machine learning book. This also is really very interesting textbook. And this is our panel A is the original data. Panel B are the 2 principal components displayed as vectors, and panel C is the data projected on the first principal component, right? If I want to plot this in 1 dimension, this is going to be my PC1, and I have these orange dots. Are we good? Okay. So now let's continue the discussion of the terminology in principal components. So projection errors. What are the projection errors? Projection errors are perpendicular distance, or our Euclidean, our friend Euclidean distance between the data points and the principal components. Perpendicular distance of the data points, and let's say this is my principal component 1 and principal component, right? So this is our projection error. Then a spread. A spread is the variation of the data along the principal component. So I can think of this thing as a spread of the data. The wider the spread, the more variation I have alongside a PC. Are we good? So technically, we can call this a spread. We can call this a spread, this a spread. But different textbook define it differently. So I just want you to think of it, look at the big picture. The variation alongside the PC, think of it as a spread. Okay. So what is the objective function in PCA? The objective function in PCA is to minimize the projection errors, these ones, or equivalently maximize the spread. I think this visualization is going to help you. So what is the objective function? We know that the answer is this, right? This is the answer, PC1. But I want you to pay attention to these red lines. So the red lines are the projection errors. Where is it minimized? Look at that. Right here, right? Then I want you to look at the spread of these red dots. Where is it maximized? It's minimized here, right? The spread of red dots. Now, when it goes to look at the spread of red dots, here it's maximized. So this is equivalent. Minimizing the projection error is the same as maximizing the spread. Mathematically speaking, it's easier to formulate this part, maximizing the spread, rather than minimizing this perpendicular distances. Are we good? But they're looking at the same thing. Okay. Please let me go to the next page. All right, so we're done with terminology. I think the rest of the class is going to be very straightforward because now we know the core of principal components. Now let's see how we can formalize all the things that we saw. Right? We know the objective function. Now let's quickly put it in mathematic form. Principal component analysis, this is a definition of PCA. We are adding the term analysis. So that so far we were talking about principal components, now we're talking about principal component analysis. Dimension reduction aims to represent the data with many typically correlated features by smaller set of features that a seal does well in describing the data, right? So instead of working with hundreds of features, I want to work with 3 features that explain the 80% of the variation of the data. This is awesome, right? When there are many features in the data set, visualization of the data or finding or fitting the models to the data may become extremely complex and noisy, right? Just always remember, think of that example of 2,000 features. PCA is used to summarize or transform highly correlated features of data into a few main uncorrelated components. How do I know that it's uncorrelated? Because PC1 is orthogonal to the PC2, orthogonal to PC3, and etc. This is really cool. Okay, the PCA algorithm orders the eigenvectors from highest to lowest, right? And how does it order the eigenvectors? By looking at the eigenvalues. The one with the highest eigenvalue first, it's explaining the variation alongside whatever that eigenvector is, and the next one, the next one, the next one, according to their usefulness in explaining the total variance in the data. And that usefulness in total variance is our eigenvalues. Is that clear? Remember that circle that I showed you, when the eigenvalue was largest, AB was largest. So the variance alongside that, that direction was largest. So here's another example. So let's say we are in 3 dimension. I want you to sort these eigenvalues for me. I'm going to show them with lambda, right? So this is lambda green, lambda red, lambda blue. Tell me which one is the largest. What is lambda? This is eigenvalue. Eigenvalue is the, look at that, total variance. So red is the largest, right? Does everyone agree that lambda red is largest? What is the next one? Probably green. And the last one is blue, right? So if I end up reducing 1 dimension, which I'm going to drop? This one. So I go from 3 dimension to 2 dimension by picking the first 2 principal components. Okay. So what does it mean? Maybe the red is explaining 60% of the variation. The green is explaining 20% of the variation. And the blue is explaining, let's say, the remaining 20%. Or let's say 30, 10. So the first 2 is going to explain 90% of the variation of the data. I reduce the dimension. Okay, now let's talk about the details. The PC1 of a set of features, we have x1 through xp, let's call it xp, right? Is a normalized linear combination of the feature that has the largest variance, right? So why do we need to normalize it? Because, guys, remember, if you're calculating do you remember I told you that the principal components are a linear combination of all the features, right? I need to normalize them because otherwise, if this data can be large numbers, the PC can be a very, very large number. I cannot compare apples to apples, right? I need to make sure that these phi, not theta, sorry, that's phi or phi. These phi's are normalized, and then I call them loadings, loading factors. So these are the loadings of the principal components. So the loadings are normalized like this. The sum of square of the loadings should be equal to what? This is just a normalization. Just divide them by the sum of square of the phi squared, you get this number. Okay. Okay. And the elements phi 1, 1 through P1 are called loadings. So each principal component is a linear combination of all the features with some loadings, right? We're going to look at a numerical example. It makes a lot more sense. Note that X features are standardized. This is an easy question. Why? Why do we need to standardize the features here? Guys, remember, I gave you a hint. Wherever you wanted to, you were wondering, should I standardize or not? Look, if you're calculating a Euclidean distance, you would be better off standardizing, right? This is what we're doing. So we were what were the projection errors? You remember, we were calculating the Euclidean distance between observations and the principal component. Okay. So the loading vectors phi1 or phi1 defines a direction in feature space along which the data vary the most, maximizing the variance in that direction. Does this make sense? This is just a repetition of what we had. But I want to define the objective function mathematically. This is the objective function. We are maximizing the variance alongside the PC1. And this is the equation for variance. How do I know that this is the equation for variance? Because remember, guys, we are standardizing things. So if I come up with the, let's say I have a variable z. What is the variance of z? Variance of z is going to be, I don't know, summation of zi minus z bar. If z is standardized, I don't have this part, right? So it's zi to the power of 2. So this is my zi to the power of 2, right? So this is the formula for variance. So I'm maximizing the variance by finding these loadings. This is my constraint. Again, we're not going to calculate these things manually. There's a method called SVD to find the thetas, to phi's for us. But I hope that you realize what's the objective function. We are trying to maximize. This is what we're going to do, right? These loading vector is going to maximize, find a direction in the space that data are varying most, right? Maximizing the variance in that direction. Maximizing the variance in that direction. What is that direction? These phi's are going to tell us what is that direction. This is, where is that? Where's that visualization? I believe it was here. This is what we're doing here, this one. So that objective function is finding the phi's, the loadings, and it's going to, the maximum is going to happen here. Right? The maximum variance is going to happen here, maximizing the spread. Maximizing the spread is the same as maximizing the variance alongside that principal component. Okay. All right. So that was the mathematics. I think we're done with the hard part. Now let's look at some numerical examples and wrap it up. So this is an example from ISLR textbook. The data is USA arrest data set. It contains numbers of arrests per 100K, 100,000 residents for each of the 50 states, right? And these are the features. We have 4 features: murder, assault, rape, and urban population, right? I handpicked 3 of the observations in the data. Please. So for example, for California, Florida, and New Hampshire, this is the data, right? We have murder, and these are standardized. So I already standardized a feature. So the murder 0.27 means that this state, the murder rate is 0.27 standard deviation higher than the average, right? Then assault, urban population, etc. Florida, then New Hampshire. So for example, you can see in terms of murder rates, so Florida is worse, and then New Hampshire maybe is best, at least among these 3, right? So this is our data set. This is my feature space, X1, X2, X3, X4. I want to reduce the dimension of this data from 4 to 2. Why? Because I want to visualize. I want to come up with a plot that I can see the states, and then I can cluster them, find a pattern, right? Without knowing anything about the data, right? Okay, when I say without knowing anything, I mean numerically, right? Visually, we are looking at the data. So PCA was performed, and after standardization of each feature. So we standardize the features, and we apply the PCA, and the loadings are as follows. So these are so what are the PC1, PC2? Look at that. We want to go from 4 dimension to 2 dimension, and these are the loadings of each X, right? So this is my X1, X2, X3, and X4. These are little phi's. Phi 1, 1, phi 1, 2, phi 1, 3, and etc. Right? So these are the loadings. And then what is biplot? Biplot displays both the PC scores and PC loadings. So the loadings are these vectors. I'm going to give you numerical examples. And scores are the final values for those states in the 2 dimension, right? So look at Florida, for example. Florida is here. So Florida, after, I could not visualize Florida in 4 dimension, but now I can visualize it in 2 dimension because I'm looking at their score. All right, so this is Florida, this is New Hampshire, and this is California. So maybe, I don't know, at the end of the day, when I look at this data, I say, okay, maybe these states are different than these states. I don't label them yet. I don't want to call them anything. I don't want to label them. But I know that maybe the behavior of the states, I can classify them in 2 groups in whole US. Does that make sense? We're going to see how we can come up with these numbers in Python next class, but I want you to, at least numerically, hopefully it makes sense, come up with, understand the terminology. So these are the principal components. These are the loading vectors, phi. So this is the entire thing is phi1, phi2. And the scores are each score that after we can dedicate to each state, right? So for example, for Florida, I don't know, let's do Florida very quickly. Let's do Florida, the score of Florida. We're going to do this thing in Python with one line, but let's see what does it mean. So what are I'm going to do Florida in direction of PC1. So I'm going to focus on these ones. So these are the loading, 0.53, multiply the loading of murder. So what is murder? Florida, 0.27. Plus 0.58, multiply assault, 1.26. Plus, oh, sorry, these numbers are for California. Thank you so much. These are for California, right? And then 0.27, 1.75. And then plus, what else? The last one, 0.54, multiply 2.06. If you do the math, you should get some number around 2.5. Just give it a try at home. All right, so this is the score of California along the PC1. You calculate the score of California along the PC2, and then you come up with this. So the California is going to be 2.5 and 1.9. Does that make sense? How do we do the scores? And etc. Again, we don't need to do any of these things manually, but I just want you to be aware that what is this PCA transformation is doing, going from 4-dimension to 2-dimension in a, I think, smart way, whatever.
And that's essentially where California will show up on the PCA graph.
Exactly. Yeah, this is biplot. This is PC. Look at a very good question. Look at the axis. The whole point of doing PCA is going to transform data to new coordinate axes. Now we can visualize them. Okay. Another interpretation of PCA, we can think of PCA. The PCA is a thing that finds the hyperplane closest to the observation. So this is going to be actually really interesting. Look at that. I have x1 and x2. So the hyperplane closest to the observation. So this is going to be the answer. This is our PC1. The hyperplane closest to the observation is called your first components, right? And the distance or perpendicular distance. Are we good? In 2-dimension, in 3-dimension, something like this. It's a hyperplane, right? Here's a question for you. So what is the difference between PCA and linear regression then? Doesn't it look like a lot like linear regression? So what's going on? What's the difference? There are two things that you should pay attention. First of all, this is x2. This is not y. The second thing, in linear regression, did you do something like this? And you wanted to calculate residuals? You calculate this distance. That's the difference, right? So you did not calculate the perpendicular distance. You calculate the distance from y minus y hat. That was not perpendicular. Are we good? So pay attention to the difference between, what's the difference between this interpretation of PCA and linear model? All right. Okay, now let's see what is a Scree plot. So a Scree plot is going to be very useful, and actually it shows the proportion of total variance in the data explained by each principal component, right? So this is, I already talked about it. So for example, if you end up, imagine you have 4 dimensions, and then PC1 explain, I don't know, 60%, PC2 explains, let's say 20%, PC3 explains 15%, and PC4 explains, you should add up to 1. So 80, 80, 95, 5%. Okay. If we can plot them, right? We can look at the contribution of each principal component to the total variance of the data, and then look at the ratio. We call it proportional variance explained. I think this is very straightforward, right? Yes.
So with data like that, would you, like, I'm sure there's some type of threshold you can use, but I feel like you would use PC1, 2, and 3 and drop PC4?
Yeah, good question. So rule of thumb, again, it depends on the context. You know me, I don't like to work with rule of thumbs, but it says if it is above 85%, it's good. But we'll see in the Python next class that it's only explaining 60%, PC1, PC2, but it's doing the awesome job. Okay, again, it depends. Right? But usually you pick the principal components up to a level that it's explaining 85%. And if you want to do it for visualization, you don't go beyond 3-dimension, right? Why would you? Or you don't go beyond 2-dimension, why would you? Even though it's explaining only 60%. So this is our proportion variance explained. Look at that. Component 1, 60%, component 2, 25%, 3, 15%, then 4, 5%. If you want to go with the first two you look at the cumulative PVE or proportional variance explained. The cumulative is around, I don't know, here my numbers were kind of off, so it's 85 maybe. So if the two components give me 85% variation, I'll pick PC1, PC2 and be done with it. Does that make sense? Okay. So what is the optimal number of PC here? Why cannot we use cross-validation? So the answer to this one, again, if you want to use that rule of thumb, maybe 85 to 90 is good. So you can say the answer is 2. Why cannot we use cross-validation? This is a tricky question. Actually, I like it. Why cannot we use cross-validation? Do you remember we wanted to? Yeah.
Is it the same thing where we don't have a Y?
Very good. What are you evaluating? Nothing.
Yeah.
PCA, you cannot predict. You're not making any predictions. You're not validating anything. You cannot say that the model is doing a good job or bad job. Guys, remember, this is unsupervised learning model. The goal is not to make prediction. The goal is to not say that, okay, the performance of the PCA, it doesn't make any sense to say that the performance of the PCA is good or bad because we are not making any prediction, right? Okay, so that was a cross-validation. How are we doing in terms of time? 5 minutes. Let's move on and see how many more slides we can cover. So pros and cons. So obviously, one of the biggest advantages of doing PCA is reducing the dimension, right? Reducing the number of features. To the most relevant predictors is very useful in general. So dimension reduction facilitates the data visualization in 2 or 3 dimensions, right? And we're going to do all these things before training the models, right? Before training another supervised or unsupervised model, namely clustering models. We can do PCA as part of the explanatory data analysis, EDA, to identify pattern and detect correlation. Does that make sense? At the end of the, well, we're going to look at some applications that's going to drive our point home. Machine learning models are quicker to train in lower dimensions, so this is no surprise, right? Remember our KNN, cares of dimensionality. So if the dimension is 200, you're done with KNN. But if the dimension is 3, KNN is going to do a good job. Regardless of the model, the smaller the number of features is going to be faster. There is no surprise here. Okay, and what are the cons? It's hard to interpret. Remember, what is PC1? PC1 is a linear combination, so x1, x2, and etc. Let's say a linear combination of hundreds of features. There's no interpretation, right? Okay, now I'm going to explain, go over one of the applications, and we're going to stop here. So this is actually one example from the text from the CFA reading, which is really, really interesting. So, and consider a hypothetical diversified large cap portfolio. So our large cap portfolio is 500 indices, right? 500 equities, right? And so we have 2 portfolios, DLC, diversified large cap, 500 stocks or equities, and very large cap. The very large cap is top 30 giant companies, right? Large cap means market cap. And when I say large cap means its size. So Apple, Microsoft, Google, Tesla, and etc. The 6th one is Bitcoin, which we don't know what is it, right? As a side note, Bitcoin passed in terms of value, passed the British pound, which is insane. Yeah, 1.some trillion. Okay, so our DLC 500 can be thought of as a diversified index of 500 large cap companies, and DLC 30 largest publicly traded companies, right? So these are the 2 portfolios that we have. And the data set consists of this index prices and more than 2,000 fundamental and technical features. So this is what in finance we call it factor zoo, right? So my own research was, I came up with one of these factors in my PhD years, right? So one of these 2,000 maybe is mine, right? So you can think of that, this is literally factor zoo. Which one is contributing more? Which one is, so it doesn't make any sense to run regression on 2,000 factors out there, right? So this is a very good example that we should do principal component analysis to reduce the dimension of the data. And of course, multicollinearity is inevitable. And to mitigate the problem, the PCA can be used to capture the information and variance in the data, right? Look at the beauty. So the following Scree plot show that the 20 principal components generated out of those 2,000, right? The first three together explain about 90% of the DLC 500 and 86% of the VLC 30. So out of 2,000 features, the first three in the DLC portfolio explain 90% of the variation. And the first three in the VLC portfolio explain 86% of the features. So we go from 2,000 dimension to 3 dimension. Now I can apply machine learning models, whatever, random forest, logistic regression, KNN, and then make predictions. Yes, Ryan.
Is there a reason why we only go up to 3? I know we were talking about you can't visualize 3, but like,
yeah,
what would be the issue with going up to 4?
Very good question. Actually, I leave it as a homework. You know, in your homework, you're going to work with a market data set for 1,200 equities over the past couple of years, and you have 100 features. And I will ask you, what is that, and what is that number of principal components that's going to explain this threshold of the variation, right? And the answer is more than 3. It's way more than 3. So it's still better go from 2,000 to 20,
right,
even if you want to lose the visualization, right? Yeah. Well, again, if you want to visualize it, stick to 2 or 3. Other than that, just go up to when the threshold of explain is 80%, 85%.
Gotcha. Okay. So it doesn't matter.
No, it doesn't matter. Yeah. If you don't want to do visualization, it really doesn't matter.
So,
but
so the whole point of PCA isn't necessarily visualization.
Oh.
It's more so just for to remove the curse dimensionality.
Both. Yeah, both. Because I think Grayson asked a very good question. We didn't get to answer those one. I'll leave it for next class. That why do we? My memory doesn't serve, so, but it's related to that. So, oops, oh, this is not the updated version. So basically the idea is that with the computation power today, correct me if I'm wrong, right? So with more, the XGBoost that can handle large dimensions, why do we even care about PCA, right? This is a good question. The answer is that we want to do visualization, right? Okay. But again, remember, for a data set that has 20 features, maybe it doesn't make sense to do PCA when you have XGBoost. But it has 2,000 features. It really makes sense. Okay. Okay, we're almost done. So I'm going to leave these 2 next slides for our last class, and then next class. So basically, we're going to start from here. Okay, thank you guys, and hopefully, just save your question for our next class. Next time, we're going to go over the Python part, and we'll see how we can apply all these things in Python. And as you can guess, the Python part is the easy part.